lecture, we shall discuss some problems related to rotational spectroscopy. Problem number 1. What is a change in the rotational constant B when hydrogen is replaced by deuterium in the hydrogen molecule? So we are going to calculate B dash. Here we have denoted the prime symbol for isotopically substituted hydrogen. So B is the original atom and B dash is the isotope. We know that B equals H divided by 8 pi squared IC. So B is directly proportional to 1 divided by I. And similarly for isotope, B dash is directly proportional to 1 divided by I prime. And of course we know that I equals mu R squared, and bond R is nothing but the bond length. When you are going to substitute isotope, bond length remains unchanged. That we know already. So I is directly proportional to mu. Similarly, I dash is directly proportional to mu dash. So keeping these two, we can have B divided by B dash equal to I dash divided by I, which is equal to mu dash divided by mu. In the problem as it is given as mu equals mh divided by 2. Mu dash equal to md. D stands for deuterium. H stands for hydrogen. So mu dash equal to md divided by 2, which is equal to mh. Md divided by 2 is nothing but mh. So B divided by B dash equal to mu dash divided by mu, which is equal to, for mu dash we can write mh. So mh divided by mu is nothing but mh divided by 2. This mh and this mh get cancelled. We have divided by 2, that will go to the numerator, which is nothing but 2. So B dash equal to B divided by 2. So change in rotation constant is nothing but B divided by 2. Now we'll go for the second problem. The first line in the rotational spectrum of carbon monoxide has a frequency of 3.8424 centimeter to the power minus 1. Calculate the rotational constant. We are going to calculate B, and hence the CO bond length, which is nothing but R in carbon monoxide. Avogadro number is given as 6.022 into 10 power 23 per mole. It is given as the rotational constant is given 3.8424, which is nothing but 2B. So 2B equals 3.8424. Dividing by 2 will give us B, which is nothing but 1.9212 centimeter power minus 1, which is equal to 192.12 meter power minus 1. And of course, we'll have to calculate now R, which is nothing but bond length. And we know that I equals mu R squared, which is equal to H divided by 8 pi squared BC. So I is nothing but H divided by 8 pi squared BC. So equating these two expressions, we can have R squared equal to H divided by 8 pi squared mu BC. So substituting all the values. And of course, we know that mu equals m1 m2 divided by m1 plus m2. So this is m1 and this is m2 divided by m1 plus m2 multiplied by Avogadro number. So this simplifying that will have 1.1385 in 10 power minus 23 grams. And converting this one into kgs, we have 1.1385 into 10 power minus 26 kg. So, and of course we know that R square equals H divided by 8 pi squared mu BC. So substituting the value for H here and substituting the value for mu, substituting the value for B and C, on simplifying, we will have 1.29, 1.2792 in 10 power minus 20. This is nothing but R squared. Taking the root, that will give us the bond length, which is nothing but 1.131 angstrom. Problem number 3. What is the average period of rotational of HCl molecules if it is in the J equals 1 state? So average period. So we are going to calculate now T. The internuclear distance of HCl is given as 0.1274 nanometer. Given the mass of the hydrogen and chlorine atoms are 1.673 in 10 power 27 kg and 58.06 in 10 power minus 27 kg respectively. Rotational energy of a classical rotor, which is equal to half I omega square. Rotational energy of a quantum rotor is nothing but h square divided by 8 pi squared I j into j plus 1. Equating these two will give us half I omega squared equal to h square divided by 8 pi squared I times j into j plus 1. So here omega squared equals h squared divided by this 2 and the 8 will get cancelled as 4 and I comes to the right hand side, we'll have I squared. So omega squared is nothing but h squared j into j plus 1 divided by 4 pi squared I squared. So first we will find out I is nothing but mu r squared, and of course we know that mu equals m1 m2 divided by m1 plus m2, which is the reduced mass. So for hydrogen we can have 1.673 into 10 power minus 27 kg. For chlorine it is 58.06 into 10 power minus 27 kg. Substituting these values, we will have I is nothing but 0.0264 into 10 power minus 45 kg meter square. And we know that omega equals root of h times root of j into j plus 1 divided by 2 pi I. So substituting all the values here, we will have the value of for omega, which is nothing but 56.5116 into 10 power 11 per second. Now period of rotation, it is nothing but t equals 2 pi by omega. So substituting the value of omega here in the expression of t, we will have 1.1112 into 10 power minus 12 seconds. Now we will go for the problem number 4. The first rotational line of carbon 12 O16 is observed at 3.84235 per centimeter, and that of isotope C13 O16 is given as 3.67337 per centimeter. Calculate the weight of carbon 13. So we are going to obtain the mass of the isotope, assuming a mass of O16 to be 15.9949. So let B be the rotational constant of an atom and B dash be the rotational constant of an isotope. Then the ratio of these two is given as B dash divided by B equals 3.84235 divided by 3.67337. They are as it is given in the problem, which is equal to 1.046. Now writing B for the rotation constant for C12O16 and B dash for C13O16, then the ratio of B and B dash is given as B divided by B dash equal to I dash divided by I equals mu dash divided by mu. So let the atomic weight of carbon 13 be 13 m. So we'll have mu dash by mu dash by mu, which is equal to, we know the formula m1 m2 divided by m1 plus m2 for mu dash, and for mu it is just a division is there. So we can write m1 plus m2 divided by m1 plus m2, and this reduced mass is for isotope and this reduced mass is for the original atom. So mu dash by mu, which is equal to, as I said, this is for isotope, so M13C and M O16 divided by M313 MO16 multiplied by, this is for the original atom. Now substitute the required values. So substitute the given values. We have M multiplied by 15.9949, which is given there, divided by M plus 15.9949 multiplied by 12 plus 15.9949 divided by 12 multiplied by 15.9949, and this is for isotope and this is for original atom. Now cancelling this term out, so this term 15.9949 and here also we have 15.9949. Simplifying we have, and already we have calculated mu dash by mu, which is given us, which we have obtained as 1.046. So the remaining term will be M multiplied by 27.9949 divided by 12 multiplied by M plus 15.9949. Cross multiplying. So when you cross multiply, we will have this expression this 1.046 multiplied by 12 multiplied by m will give you this. So 12.552 multiplied by 15.9949 is here, which is equal to m times 27.9949. Now you just bring this term to this 12.552 that side. So we will, I'm taking m common out, so that will give us m times 27.9949 minus 12.552, which is equal to, so this term will give us this second term. Second and third term will give us 200.768. So m equals 200.768 divided by, after subtracting, we will have 15.4429, which is equal to 13.001. So this is your atomic weight of carbon isotope. Rotational and centrifugal distortion constant of the HCl molecule are, so 10.593 per centimeter and 5.3 into 10 power minus 4 per centimeter, respectively. Estimate the vibrational frequency and the force constant of the molecule. So B is given and D is given. We are going to calculate mu bar square, thereby mu bar. And mu bar square equal to 4B cube divided by D. The data are given in the problem. So 4 times 10.5933 whole cube divided by the value of D, 5.3 10 to the power minus 4 to the power 1 by 2. That will give us the value of mu bar, which is nothing but vibration frequency. So simplifying, we will have 2995.2 per centimeter. Okay, this is the correct one. 299.5 per centimeter. Now the force constant K equals 4 pi square C square mu bar square. And of course, we know all the below values. We have to calculate mu alone. And of course, the reduced mass is nothing but m1 m2 divided by m1 plus m2. So mu equals 1.01 multiplied by 1.6 in 10 power minus 27 multiplied by 35.5 multiplied by 1.66 in 10 power minus 27. So one is for hydrogen, then another one is for chlorine. So divided by m1 plus m2 times 1.6 in 10 power minus 27. On simplifying, we will get the reduced mass value as 1.6302 into 10 power minus 27 kg. So the force constant K equals 4 times 3.14 squared multiplied by 3 in 10 power 8 whole squared multiplied by 1.6302 into 10 power 27 multiplied by 2995.2 into 10 power 2 whole squared. So your K, which is equal to 519.1 Newton by meter. Now we will go for the sixth problem. 3 consecutive lines in the rotational spectrum of a diatomic molecule are observed as 84.544, 101.355 and 118.112 per centimeter. Assign these values to their appropriate J double prime to J prime transitions and reduce the values of B and D. So we are going to calculate now first J and thereby B and D. Hence evaluate the appropriate vibration frequency of the molecule. The frequency of J to J plus 1 transition is given by this expression we have already studied for the symmetric top molecules. So the frequency mu J bar is equal to 2B J plus 1 minus 4D J plus 1. Now for the first transition, we have 84.544, which is equal to 2B J plus 1 minus 4D J plus 1 whole cube. And for the second transition, 101.355, the equation 2 is written. And for the third transition, given us equation 3. Now equation 2 minus equation 1. Our aim is to find out B and D. So first we will have to find out J and thereby B and D. So now equation 2 minus equation 1 will give us this equation 16.811 which is equal to 2b minus 4d j plus 2 whole cube minus j plus 1 whole cube. Suppose if we are going to assume d is very, very smaller than that of b, then we can have 16.811 which is equal to 2b. So from this value we can get the value of b. So now 84.544, we know already this, just take this equation, so which is equal to 2b. 2b is nothing but 16.811. See here, we have 2b, j plus 1, and since d is very, very small, we can neglect this, neglect in this equation. So 84.544, which is equal to 2b times j plus 1. Instead of 2b, you substitute 16.811. So 16.811 times j plus 1. And simplifying, we can get the value of j, which is equal to 4.03, which is equal to 4, corrected to the integer. So therefore, therefore the line at 84.544 centimeter per minus 1 corresponds to j equals 4 to j equals 5, as it is given as j tends to j plus 1. So j equals 4, which tends to j equals 5 transition. 1 at 101.355 centimeter per minus 1 is due to j equals 5 to j equal to 6. And the last one is 118.112 per centimeter is due to the transition from j equals 6 to j equals 7. With these values, so we have found out now j. With these values, equation 4 is obtained now. So already we have found out now j. This is for j equals 4. So j equals 4 means j plus 1. So which is 5. So substitute in this equation 84.544, which is equal to 2b. Instead of j plus 1, you can substitute 5 minus 4d. Here it is nothing 4 plus 1, 5. So we have 2b multiplied by 5 minus 4d multiplied by, here it is j plus 1. So 4 plus 1, 5 cube, which is equal to 125. So the next equation becomes 101.355, which is equal to 2b j plus 2, so which is number 4 plus 2, so which is nothing but 6, minus 4d, 4 plus 2, which is number 6, 6 cube is nothing but 216. Now we have equation 4 and 5. Two equations are there, two unknowns are there. We can solve easily to get the unknowns b and d. Now equation 4 multiplied by 6. Equation 4 multiplied by 6 will give this equation, and equation 5 multiplied by 5 will give us this equation. Now we just subtract from this equation to this equation. This 60b and 60b will get cancelled. So we have 507.264 minus 506.775 will give us 0.489, and this is minus and this will become plus. So when you are going to simplify, you will have 1320d. So d equals 3.705 into 10 power minus 4. You substitute any one of the equations instead of d, and you can get the value for d. So we will have 507.264, which is equal to 60b minus, here it is 3000 times multiplied by 3.705 into 10 power minus 4, and b equals 506.153 divided by 60 will give us 8.436. So we have found out now b value and d value. We want to find out nu bar frequency, then use this relation d equals 4b cube divided by nu bar square. So nu bar square equals this one, and simplifying we will have nu bar equal to 2547.6 per centimeter. We'll go to the next problem. The observed rotational spectrum of HF shows j equals 0 to j equals 1 absorption at 41.11 per centimeter. The spacing between adjacent absorptions is 40.08 per centimeter around j equals 5 to j equals 6 transitions, and only 37.81 per centimeter around j equal to 1 to j equal to 10 to j equal to 11 transition. Calculate b value and I value from these three given data. So you have to calculate the b values for these two transitions and I values of these three transitions. what explanation can you give for this variation? So j equal to 0 to j equal to 1 given. These are the data which is given. J equal to 0 to j equal to 1, which is equal to 2b, which is equal to 41.11 per centimeter. So from this expression, we can get the value for b, which is equal to 20.56 per centimeter. Similarly, j equal to 5 to j equal to 6, 2b is given. We can get the value for b. Similarly, j equals 10 to j equal to 11, 2b is given. We can get the expression for value of b as 18.91 per centimeter. And of course, we know the relation b equals h divided by 8 pi square IC. And for the first one, we have b equals 2056 per meter. So we have converted into centimeter into meter, which gives us I equals h divided by 8 pi square b times c, which is equal to 1.362 into 10 power minus 47 kg meter square. Similarly, we can get the moment of inertia for I using the same relation, h divided by 8 pi square bc, and we can get the moment of inertia for the next transition b equals 1891 e to power minus 1 using this relation. Including centrifugal distortion, the expression for the frequency of a transition is given as mu bar, which is equal to 2b j plus 1 minus 4d j plus 1 whole cube. As a term, the second term, 4d j plus 1 whole cube is always positive. The separation between energy levels decreases as j increases. In other words, in the excited state, the amplitude of vibration of the atoms is expected to be larger, which increases the moment of inertia I equals mu r square.